Hey everybody, I hope you're having a fantastic day, staying well, and rocking your quarantine. Welcome to another logic video. Recently, we've learned how to symbolize statements for truth tables. We've been introduced to truth tables, and we've learned the truth tables for 5 logical operators. In this video today, we're going to be learning how to construct truth tables for arguments in order to determine whether an argument is valid or invalid. If you'd like to follow along, there are notes that go along with this video. They're posted on Canvas. They're called Truth Tables for Arguments. So you can pause the video to pull them up on your screen or print them out, whichever you prefer. Now let's go ahead and jump into it. You already know that in order to use a truth table, you need to first symbolize the statement or argument. So far, though, we've only been symbolizing statements. Fortunately, symbolizing a whole argument is not that much more complicated. You just need to add a couple more things. The first thing we'll add is commas. Commas are going to be used to separate premises from each other. You'll also want to add a little bit of extra space in between premises in order to easily be able to tell when one ends and the other begins. And the second thing we'll add is the triple dot symbol. As the name suggests, the triple dot symbol is just 3 dots in the shape of a triangle. We'll put this in front of our conclusion. This just helps us distinguish the conclusion from the premises more easily, especially if your work area, your paper starts to get really cluttered or messy. Let's go ahead and try these out with an example. For that, how about we take a look at my desk? All right, this argument is from page 311 in your book. It's number 89. The first sentence is a straightforward conditional. If Lincoln is 8 feet tall, then Lincoln is over 7 feet tall. Using E and S for the atomic statements, this becomes E arrow S. The next sentence is a negation, but it is not the case that Lincoln is over 7 feet tall. We'll ignore the but since it's excess verbiage. The atomic statement gets replaced by an S, and we'll put a tilde in front of it to symbolize it is not the case that. Since the 2 statements we have so far are premises, we'll separate them with a comma. And hopefully you didn't forget to leave some space between the premises. Our last sentence starts with it follows that. In this phrase, it indicates that here comes the conclusion. So in order to indicate our conclusion, we'll make sure and use our triple dot symbol in front of it, remembering to leave adequate space in between it and the last premise in order to distinguish it. So our conclusion is Lincoln is not 8 feet tall, so we'll symbolize it as tilde E. And that's our symbolization. Now that we have the argument symbolized, we can create a truth table for it in order to determine if the argument's valid or invalid. Before I walk you through how to create one step by step, though, first, let's look at a completed truth table, and I'll talk about the way truth tables work so you have a better understanding of why we do each step the way we do when we're constructing one. Here is a nice truth table. So how do they work? Well, truth tables for arguments are very similar to the truth tables we've already seen for logical operators. The idea behind them is that you want to consider every possible scenario and see if your premises guarantee your conclusion. If they do guarantee it, the argument's valid. If they don't, the argument's invalid. The thing on your table that represents a scenario, a possible scenario, is going to be a horizontal row on the table. So each horizontal row is going to represent one possible scenario. And the idea is all together, all the rows represent all the different possible scenarios. So one possible scenario, what that is it's some combination of truth and falsity for your atomic statements. The idea is you want every possible combination of true and false to get its own row. More on how to actually construct these rows in a minute, but for now, the idea is if any of these rows or scenarios results in all your premises being true on that row, while your conclusion is also false on that same row, then you know that the argument is invalid. Instead, though, if none of the scenarios, none of the rows have that result where all premises are true and the conclusion's false, there's none of those, then you know that your argument is valid. So why do those results indicate validity and invalidity? Well, they indicate this because, remember, validity is about truth being guaranteed. If there is a possible scenario in which all the premises are true and the conclusion's false, then you know that your argument's premises don't guarantee your conclusion. In some scenarios, your conclusion might be true, but if there's just one scenario in which your premises are true and your conclusion's false, then you know that these premises don't guarantee your conclusion. So your argument is invalid. If, however, there are no scenarios, zero rows, in which all your premises are true and your conclusion is false, then your premises do guarantee your conclusion. Whenever your premises are true, your conclusion is true. That's guaranteed. So your argument is valid. Now that we have a better idea of how truth tables work, let's go ahead and see how to construct one step by step. And we'll use the argument we just symbolized. After drawing our dividing lines, we focus on the left side of the table. Above the line, place the capital letters of the atomic statements. Put them in sequence from left to right in the order they appear in your argument. And you only write each letter once on the left side of the table, even if it occurs multiple times in your argument. Now below the line, we need to write out every possible combination of truth and falsity for our statement letters. It's pretty easy when we only have 2 statement letters, but it can get more confusing when we have more than 2. So later I'll show you a method for doing that, but for now we'll just do it intuitively. One combination of true and false for our statements is of course true and true. There's also E is true and S is false. There is E is false and S is true. And of course, there's when both E and S are false. Now we have every possible scenario for truth and falsity for our argument represented by its own row. Now we need to complete each row on the right side of the table to see how each scenario plays out. In order to avoid confusion with all the T's and F's that there might be on each line, what you first want to do is draw an elongated circle to mark the main operator of each premise and the conclusion. What this is going to do is it creates a column under each statement, and it's going to be the T or F that will be inside these columns that we're going to look at when later we go on to read our table to figure out if the argument's true or false. And these circles, they can just help prevent confusion and mistakes. Trust me, it'll help you out a lot. All right, on the first line, the first scenario, E and S are both true, and that's going to make the first premise true. Our second premise, not S, will be false, since if S is true, not S is going to be false. Our conclusion will also be false, since when E is true, not E is false. Now we have one scenario row is complete, and we're going to do the same for each row. So on row 2, our first premise is now false because a true antecedent with a false conclusion it's the one way to make a conditional statement false. Our second premise, it's now true because this scenario has S being false, and our conclusion will still be false. Scenario 3, row 3, we're going to have true premise, true conclusion. The first premise is true because, remember promises. Mom promises, if you get an A on your exam, I'll send you cookies. Well, here in premise 1, no promises are broken. It's like we have false, arrow, true. It's like if you fail to get an A on your exam, but mom goes ahead and sends you cookies anyways. So no promises no promise was broken. This premise is true. And finally, our fourth row, our fourth scenario, will give us true premises with a true conclusion. So that completes our construction, and all that's left is reading the truth table and marking it. To read a truth table, think of it like you're going hunting in the woods, say. Now, hunters, they hunt for all kinds of things, right? Bears, wild boar, some deer, go hunting for ducks, etc. But on our hunt, we're hunting for something very special. I sometimes call them TIFs. TIFs are of the genus invalid, and they make for a delicious supper. How do you spot a TIF? Well, they like to hide on truth tables. Look for a row in your table where all the premises are true and the conclusion's false. You want a T or T's under the main operator for all your premises, followed by an F under the main operator for your conclusion, all in the same row. That's a TIF. And it gets its name from the T's and the F that it's made out of. While you're hunting these invalid beasts, be aware that TIFs can have any number of T's, but they always have just one F at the end. If there's only one premise, it looks like this. 2 premises looks like this. 3 like this, and so on. On a hunt, all you need to find is one TIF, and that'll show that your argument is invalid. One line that meets the requirement. When you find it though, make sure to mark it. You can mark it with an asterisk, a star, a sad face, or whatever. Just make sure you mark that row over to the right that shows that your argument is invalid. I mean, you don't want your invalid prey getting away, do you? If your hunt was successful, that means the argument's invalid, and you can go ahead and write invalid. If you don't find any TIFs, then your argument is valid, and you should write that. Now let's look back at our example argument and go hunting for TIFs. Do you see any? Row 4 has all true premises, but the conclusion is true, so that doesn't count. It looks like there are no invalid TIFs on this table. So that means our argument's valid. Our truth table shows that when you consider every possible scenario for the truth and falsity of the parts of our argument, on none of those scenarios do true premises ever lead to a false conclusion. Instead, true premises always guarantee that the conclusion is true. And so this guarantee, that's what makes the argument valid. That argument only had 2 statement letters, but how do you make a truth table for an argument that has more statement letters? Well, let's go ahead and look at another example that has more. This argument is a little bit more complicated. It's got 3 statement letters. So in order to do our truth table, let's go ahead and symbolize the argument. Let's start with the conclusion. The word therefore clearly marks the last sentence as the conclusion. So let's replace the equatorial rainforests produce oxygen used by Americans. We'll replace that with E, and we'll turn it is false that into a tilde symbol to negate E. Now let's symbolize the premises. The first sentence has an if-then. If the equatorial rainforests produce oxygen used by Americans, the if part, let's turn that into E arrow. And then if we look after the comma, we have a then, so that will tell us what comes after the arrow. What it says is either Americans ought to pay for the oxygen or they ought to stop complaining about the destruction of the rainforests. The either or here tells us this is going to be a disjunction, right? So we'll use a V. On one side of the V, we'll write a P for Americans ought to pay for the oxygen. On the other side of the V, we'll write an S for Americans ought to stop complaining about the destruction of the rainforests. And we'll make sure to put parentheses around this disjunction because the whole either or statement is the then part of our if-then conditional here. Now let's do the second sentence. Ignoring but, we see either. So we know we're going to have another disjunction and we can write a V. We have either it is false that Americans ought to pay for the oxygen. So on the left side of our V, we'll write tilde P, since it is false that is a negation of P. Next we have, or it is false that Americans ought to stop complaining about the destruction of the rainforests. Here we have another negation. So on the right side of our V, we'll write tilde S for the negation of Americans ought to stop complaining, etc. Awesome, that's the whole argument, and we're ready for truth table construction. How do we construct the left side of our table in a way that makes sure we capture every combination of truth and falsity? Since we have more than 2 statement letters, it's going to be a little bit more complicated than our last example. The best way to make sure we get all the combinations is to do it mechanically, and to do it mechanically the same way each time. Here's how to do that. First, you need to figure out how many rows your table needs. The formula for this is 2 to the power of n, where n is the number of statement letters in your table. Our previous example had 2 statement letters. Our current example has 3, and of course, you'll have tables with even more. 2 to the power of 2 is, of course, equivalent to 2 times 2, which equals 4. 2 to the power of 3 is equivalent to 2 times 2 times 2, which gives you 8 rows. And to the power of 4, it's 2 times 2 times 2 times 2. And now it's 16 rows. The number you plug into n basically just tells you how many 2's you multiply together. So 5 statement letters, what would that be? Be 32. 6 would be 64, and 7, don't worry, I won't ask you to do any on the exam that are greater than 8 rows. So now that we know that our truth table is going to have 8 rows, how do we fill in the T's and F's without missing any combinations? Well, we make sure and do it the same way every time. Here's how to do it. Start under the rightmost statement letter and write T, then F, T, then F, alternating all the way to the end of the column. Then move to the column to the left and double the number of T's and F's in your pattern. So here you'll write 2 T's, then 2 F's, 2 T's, then 2 F's, and so on. Repeat it as long as you need to get to the bottom of the column. The next column, we again double the number of T's and F's in our pattern. So now we'll write 4 T's, then 4 F's, and repeat that all the way to the bottom. We don't need to repeat the pattern in our example here because we only have 8 rows in this one. But here's what a 4-letter table would look like. You can see that in each column after the rightmost column, the length of the pattern has doubled from the column to its right. The pattern continues all the way to the bottom. Now that we've completed the left side of our table, we need to complete the right. So first we draw our circles to create columns under the main operators of each premise as well as the conclusion. Then we start filling in truth values. On the first line, all our letters are true. This makes the disjunction in premise 1 true, which makes premise 1 true. Not P will come out false, and so will not S, and this makes premise 2 false. And since E is true on this line, our conclusion, not E, will come out false. On line 2, E and P are the same as before, but now S is false. However, this doesn't change the disjunction in premise 1, so premise 1 is true again. But it is going to change premise 2. Not P will be false again, but since S is false now, not S will be true. And that makes the disjunction of premise 2 true this time. And the conclusion will just be the same since E hasn't changed. I'll go ahead and complete the rest of the truth table and fast forward, but you might want to pause and see if you can do it on your own first. How'd you do? I hope you wrote the same thing I wrote. Was your line 4 the only line on which the first premise was false? The reason it's false is because that's the only line where the promise was broken. The if part is truth, but the then part is false. What's next? Hunting time. We look for TIFs. Do you see any? I see 2. Lines 2 and 3. On those lines, all the premises are true and the conclusion's false. So we mark those lines where we found the TIFs. Then, since TIFs are invalid beasts, we write invalid. Let's look at one more argument. Pause the video and see if you can symbolize this one on your own. All right, how'd you do? If you didn't get it, were you close? Now let's construct a truth table for it. Pause the video and see if you can do it on your own. Construction commencing. Now it's time for hunting. Do you see any TIFs? Any rows where all the premises are true and the conclusion is false? The fifth row gets close. All the premises are true, but the conclusion is also true, so that doesn't count. It looks like there are no rows that meet our criteria, no TIFs, so this argument is in fact valid. True premises guarantee the conclusion's true. That's it for this video. In the next video, we're going to learn abbreviated truth tables. Abbreviated truth tables do the same thing as regular truth tables, they just require less writing. In the meantime, practice doing truth tables for arguments on your own. Work through the practice problems at the end of section 7.3. That'll help you out for the quiz, the homework, and the exam. Till next time, I send all of you my best wishes. Be well, look out for TIFs, and I'll see you in the next video.